Every so often, you hear reports of sleep feeling off during solar storms, dreams that feel different, a nervous system that feels a little more on edge than usual. And these reports are usually dismissed, partially because we are taught that Earth's magnetic field is too weak to matter, too weak to influence biology in any meaningful way. But my own experience suggests, and perhaps yours, that there might be more to it. So I wanted to do my own dive into the literature and see what it actually shows. Because if a changing magnetic field is truly irrelevant, that should be a pretty easy thing to prove. But if the brain responds, even subtly, then the conversation changes. Luckily, that is exactly what one 2019 study set out to test. In eNeuro, a group of neuroscientists asked a simple question: does the human brain show any measurable response when an Earth strength magnetic field changes around it? To test this, volunteers sat quietly inside a shielded room. No lights, no sounds, no movement, no cues of any kind. Then around their heads, the researchers generated magnetic fields equal in strength to Earth's natural field and rotated them in controlled directions. The coolest thing is, nothing dramatic happened. No one felt anything. No one reported any sensation at all. But their brains did. Under specific field conditions, the researchers saw a consistent drop in alpha band activity on the EEG, the brain rhythm often linked to relaxed wakefulness. When alpha drops, it usually means the brain is responding to something, even if you're not consciously aware of it. What makes the result harder to shrug off is that it was selective. When the researchers ran the same rotation pattern but flipped the vertical component, the alpha drop disappeared. Same strength, same timing, same equipment, just different orientation and a different outcome. So it was not just any magnetic change that mattered. The response showed up only when the field had the right geometry and polarity. And because of how the experiment was designed, the authors argued it could not have been explained by sound, heat, electrical induction, or a generic artifact of the setup. They were careful also not to claim purpose or function, but the core point is clear. Under controlled conditions, the human brain showed a measurable response to a rotated Earth strength magnetic field without conscious awareness. So, how could that be happening? How could a field this weak register in biology at all? If you think in the usual way, it should not. Earth's field is nowhere near strong enough to heat tissue or push currents through the brain in any obvious way. So, if the effect is real, something in the body has to be able to register the field in a subtle way. In biology, there are two broad ways that can happen. One is material. If you embed magnetic material in tissue, the field does not need to be strong to matter. The field simply needs to provide orientation. In this scenario, the magnetic particle can align, the structure can shift slightly, and that tiny physical change can become a biological signal if the surrounding cells are sensitive to it. And we know magnetic material exists in humans. Researchers have reported magnetite crystals in human head tissue in large numbers, on the order of millions of crystals per gram in some measurements. That fact does not tell us what it is doing, but it makes the material pathway physically plausible. The other is chemical. Some reactions depend on the spin state of electrons. In certain molecules, magnetic fields can bias the balance between reaction pathways. This sounds abstract, but the point is that a field can nudge chemistry without heating anything. The nudge can be small, but real. So if the brain is responding to Earth strength field changes, the mechanism does not need to be dramatic. It could be a subtle physical coupling through magnetic material. It could be a subtle chemical bias in specific reactions. It could be a combination. But at this point, we do not know actually which one of these pathways, if either, is doing the work in humans. So for now, we leave the mechanism an open question, which would not be the first time for biology because it does have a habit of doing things before we know how to describe them. In other organisms, magnetoreception is real and better understood. Animals can use features of Earth's magnetic field to orient and navigate, and the full story of how it happens has taken decades to piece together. In some species, magnetic crystals like magnetite appear to play a role. In others, chemistry and light sensitive proteins are part of the story. The details vary, but the lesson is consistent that a weak field matters to other living systems, and that may include humans. In general, Earth's magnetic field is stable, but there are some days when Earth's environment shifts. The overall field can increase slightly, but more importantly, it can become more variable and change direction as the magnetosphere is pushed and distorted. This happens during periods of solar activity when energy and charged particles from the sun interact with Earth's magnetic shield. Disturbances can build and unfold over hours to days, creating a magnetic environment that is less steady than usual. And that is often when the reports show up. Sleep feeling off, dreams feeling different, a nervous system that feels a little more on edge than usual. So now the question becomes practical. When researchers look at these disturbed windows, do they see anything measurable in humans that shifts alongside? Or does the data stay quiet? One of the clearest signals is the autonomic nervous system, the background control layer that regulates heart rate, blood pressure, breathing rhythm, and the balance between calm and alert. A common way researchers estimate that balance is heart rate variability. HRV is the beat to beat variation in timing. It can shift for many reasons, so it is best treated as a context dependent window into regulation, not a single score of health. In the normative aging study, researchers followed 809 older men and looked at HRV alongside geomagnetic conditions. In that cohort, higher geomagnetic activity was associated with reduced HRV. In plain terms, the heart rhythm looked a bit less adaptable, as if the system was spending more time in a slightly tighter, more stressed setting during these disturbed periods. Blood pressure has also been studied in the same spirit. A 2025 analysis in Communications Medicine compiled more than 500,000 blood pressure measurements across 6 years from 2 mid-latitude cities in China and compared those readings to geomagnetic activity. They reported that blood pressure tended to be higher on average during higher storm days, with stronger associations during those periods. That does not mean that the magnetic field is squeezing blood vessels directly. It means that when the external magnetic environment is more disturbed, some internal signals tied to regulation and cardiovascular state have been observed shifting alongside it. Then there is sleep biology. If people report feeling off during disturbed periods, one obvious place to look is melatonin, a hormone tightly tied to circadian timing and sleep onset. In studies of electric utility workers, researchers measured overnight urinary excretion of 6-hydroxymelatonin sulfate, a common marker used to estimate melatonin production, and they compared it to geomagnetic activity. They reported that the higher the disturbance, the lower the overnight levels were, which could affect how easily one falls asleep or how deep that sleep feels. Now, dreams are the messiest part of the literature, but I'll share a few things I found. One long case study tracked a single person's dreams for about 6.5 years and compared dream reports during very low versus very high windows. And that data set, dreams were rated as more bizarre during low geomagnetic activity than with high, which honestly is the opposite of what I would have expected. There is also smaller work looking at sleep paralysis, and it points in different directions. In one data set, episodes clustered during relatively quiet geomagnetic periods. In another, events were preceded by higher activity. So, within this narrow corner of the literature, you can find patterns that lean both ways. So, this is not a finished conclusion. More research needs to be done. Now, let's step back and look at the picture we have built. Under controlled lab conditions, there is evidence that the human brain can respond to changes in an Earth strength magnetic field, even without conscious awareness. There are plausible biological pathways that could support that sensitivity, including physical coupling through magnetic material and subtle chemical effects, though we don't know which one, if either. And beyond the lab, there are observational studies suggesting that during periods when Earth's magnetic environment becomes more disturbed, some measurable aspects of human physiology sometimes shift alongside it. None of this gives us a single clean answer, but taken together, it does something important. It shows us the question is worthy. The assumption that a weak field cannot matter turns out to be just that, an assumption. And biology has a long history of surprising us when we look closely enough, which means the most interesting work is still ahead with better experiments, better measurements, and I bet better questions. If you have noticed changes in your own sleep, mood, or nervous system during periods of high solar activity, I would genuinely like to hear about it. And if you want to keep exploring this with me, please tap the notification bell. In the next episode, we explore specific locations where magnetic conditions are unusual and examine what anomalous things people have reported. Until next time, take care.